Okay, so we've seen how to walk through or to go through step by step of calculating the pH of a buffer solution. Um, if we were to apply some of those same equilibrium principles generally to buffer systems, and we were able to go through the algebra involved, what we would end up with is an equation that we can use to allow us to calculate the pH of a solution, of a buffer solution fairly quickly. And that equation is known as the Henderson-Hasselbalch equation. Okay, and the Henderson-Hasselbalch equation, your book does a good job of deriving that equation. I'm not going to spend a whole lot of time talking about that now. We're just going to talk about the equation and how we can use it. Okay, so the Henderson-Hasselbalch equation for a buffer says that the pH of a buffer is equal to the pKa of the weak acid that is used to make the buffer plus the log of the concentration of the conjugate base of that acid. So the base of that acid divided by the concentration of the acid that was used to make that buffer. All right, this is the shortcut. This is a Henderson-Hasselbalch equation for calculating the pH of a buffer solution. So this pKa here is simply equal to the negative log of the Ka of the acid that was used, right? The Ka values, these Ka values we can look up in tables. Or they would be provided to you, or we can calculate them based on information that's given. So if we were to apply this Henderson-Hasselbalch equation to the example that we did before, this one here, what we're going to do is now substitute our values into the Henderson-Hasselbalch, which I often abbreviate as the HH for Henderson-Hasselbalch equation. We would see that the pH is equal to the negative log of the Ka, and that's the pKa. So the pKa is the negative log of the Ka, and the Ka for acetic acid is 1.8 times 10 to the minus 5 plus the log of, we have the concentration of the conjugate base, and the conjugate base concentration here was, let's see. That was 0.9 molar, and then the concentration of the acid was 1.1 molar, right? So we have the 0.9. This is not square brackets here. This is just the number. So 0.9 divided by 1.1. And if you determine this, stick this in your calculator, you'll see the negative log of the 1.8 times 10 to the minus 5 is 4.74. Okay, plus this, when we evaluate this entire thing here, that ends up being negative 0.087. Okay, and that gives 4.65 as our pH. Okay, very, very, very similar, almost identical to the 4.66 that we solved up here. The difference there of 0.01 is just due to rounding errors. So this is how we can apply the Henderson-Hasselbalch equation. Now, note when we substitute our concentrations, these concentrations here, right? They came from this table. In order to determine these concentrations, we still needed to go through and apply the stoichiometry to the buffer system to determine how much of the base and the acid and the conjugate base we ended up with in the first place. All right, so we still need to go through that step. Let's apply that same equation to the initial buffer that we had before we added an acid to it. Let's apply it to this buffer here. So for this buffer, again, the pH would be equal to the pKa plus the log of the conjugate base over the acid. Okay, so the pH here would be equal to, we know the pKa, we've calculated that already because this is acetic acid. That's 4.74 plus the log. Let's see, the conjugate base here concentration is 1. the acid there is also 1. Okay, 1 divided by 1 is 1. So what is the log of 1? Well, the log of 1 is 0. So the pH then is actually equal to the pKa. And the reason why is because the concentrations of the acid and the conjugate base are identical to each other. Okay, so whenever you have this situation occurring, the pH of the buffer will simply be equal to the pKa, because when you take the log of 1, which is what we get when we divide the conjugate base by the acid concentration, that gives us 0. Okay, let's take a look at one more example of calculating the pH of a buffer. And now we're going to take a look at having the same or very similar situation. We're going to, let's see, we're going to have a acetic acid system again. So we have a 1 molar acetic acid and it's a 1 liter. So it makes the calculations a bit easier. And also 1 molar sodium acetate, right? So we have here our acetic acid concentration is 1.0 molar. The sodium acetate, which would give us the acetate ion concentration, is also 1.0 molar. And then we're adding now to this 0.1 mole of sodium hydroxide to this buffer system. Okay, sodium hydroxide will give us the OH minus. Okay, so then that would also be the amount of the OH minus, and because this is in 1 liter of solution, okay, that'll also be the concentration of the OH minus. So 0.100 molar. So in my buffer system, right, if I add the hydroxide ion to it, right, it's the acid component of the buffer, the CH3COOH, that will react with the hydroxide to give us H2O, and then we also get the conjugate base, CH3COO minus, right? So we know now that upon addition of the hydroxide, right, we're going to have initially 1 mole of the acetic acid. We're adding how much? 0.100 moles of the hydroxide, and we also have 1.0 moles of the acetate ion that comes from the sodium acetate. After we consume, so after using up the OH minus, then this concentration goes to 0. Well, then we're going to use up the same stoichiometric amount. So we're going to minus 0.100. And we're going to make the same stoichiometric amount of the product. Okay, so we end up then with 1 minus 0.1. What is that? 0.90. The hydroxide is still 0, and then the acetate ion there would be 1.10 moles. Okay, so this is what we're going to have here after the hydroxide is consumed. Remember, all this is in 1 liter, so these are all concentrations. Okay, so 0.90 molar. This is 1.10 molar. And then we can go ahead now and use our Henderson-Hasselbalch. So the pH is equal to the pKa plus the log of the conjugate base over the acid. Okay, now we know what these are, right? So our pH, we know what the pKa for acetic acid is. We've done that a couple times already, 4.74 plus the log of the conjugate base is 1.10. The acid there is 0.90. So we evaluate that, and we end up with then the pH being equal to 4.83. All right, so the pH does go up. from the 4.74. So it does become basic, but only slightly basic. So a slight increase. And that's the whole point of a buffer system, is to minimize the change in the pH of a solution.